number of votes. Let's do this one. Two particles A and B of masses km and m respectively, where k and m are constants, they are free to move in a straight line on a smooth horizontal plane. It's a smooth horizontal plane. They're free to move on that plane. Let me make this horizontal plane. One particle is A and the other is B. Is there any other particle after that? No. We know their masses. Mass of this is km and the other one is m. It's a smooth plane, so there's no friction. A is projected towards B with speed 2u. So A is first going towards B at a speed of 2u. And at the same instant, B is projected towards A with speed u. This is going here at speed u. The particles collide after the collision. Speed of A is u. So this is before collision. And what happens after collision? Speed of A is u. And both particles move in the same direction as A's original motion. So, okay, so A is moving in this direction. And we don't know what the speed of B is. We can find that. Okay. It is given that 35% of the total kinetic energy is lost in the collision. Find in terms of u the speed of B after the collision in terms of u. And not in terms of m. So we need to eliminate m. That will already get eliminated. What other information do we have? 2u, this is u. Okay, let's start with this. So there's collision happening. Let's apply conservation of momentum first and see what happens when we do that. Momentum before collision and momentum after collision. They should be equal to each other. Momentum should be conserved. Let's take one direction positive. Let's take this direction positive. Then momentum before collision, what will that be? Km into 2u plus m into minus u, because that's moving in this direction. That should equal momentum after collision, which is km times u plus m times vb. Achha, this is one equation that we end up getting. Let's simplify this. M is appearing in every single term, right? M is appearing everywhere. So that will get cancelled. And we would just be left with 2ku minus u. That equals ku plus vb. All right. Now let's take all terms, the ku to the other side as well. And that gives us vb equal to 2ku minus ku. That will become ku minus u. This is what vb turns out to be. Velocity of B after collision. Okay. Now, what is it that we were looking for? Speed of B after collision. That's exactly what we were looking for. But we wanted to find that in terms of U. So now the problem is we also need the value of K somehow. For that, we can use the kinetic energy thing that they gave us there. They told us that 35% of the total kinetic energy is lost in the collision. Okay, now what does that mean? If the original was, let's say, 100%, then what happens afterwards? It becomes 65%, right? 35% is lost. So after collision, it is going to be 65% of the original. So we can say something like this. Final kinetic energy over initial kinetic energy, the ratio between them, what should that be? If initial was 100, we started from 100, 35% was lost. How much are we left with? 65. We'll have this ratio. Final kinetic energy of the whole system minus initial kinetic energy of the whole system. This will give us another equation. Let's input values in this. What will be the final kinetic energy after collision? We've got the masses given as well. Let's find final kinetic energy. Half, I'm starting with A first of all. Let's actually get rid of the fraction, so it'll simplify things a little. I'll multiply 100 there and this thing here, and that will give me 100 times final kinetic energy. That equals 65 times initial kinetic energy. So I just want to get rid of the fractions there. Okay, now what's the final kinetic energy? Kinetic energy of A at the end after collision. Half into mass of A, which is K times M, into V squared, speed squared, that is U in this case, U squared, plus speed of B. We can input that here, Ku minus U. 1 over 2 into mass, which is M, into speed of B, that is this thing, but that will bring a whole squared. Let's actually keep it as VB for now, and we'll see what to do with that. Let's say this is VB squared. This is the initial final kinetic energy. That equals 65 into initial kinetic energy, half into mass of A, which is K times M, into velocity, which is 2U squared, plus half into mass of the other object, which is M, into U squared. This is the initial kinetic energy. Now, this is the situation that we've got. Let's simplify this a little. 100 over 2, that will become 50, right? So we have 50 km U squared plus 50 mvb squared. That equals 65 over 2. Let's write it as 32.5, so we don't have to write fraction, into km into 2u squared. In fact, it'll become cancelled. 65 over 2 into 4, what will that become? 65 into 2, that will be 130. So the first term is going to be 130 kmu squared. Okay, and then the last term, 65 over 2, that will become 32.5 into mu squared. This is what we end up getting from this. Acha, now m is appearing in every single term, so that gets cancelled, right? M gets cancelled from all the terms. We can divide the whole thing by m. That simplifies things a little, right? But we have found that Vb is equal to Ku minus U. We have found that first from the conservation of momentum uh, equation. What we can do is we can input that here, input Vb equal to Ku minus U, and see what happens. Because that is going to simplify things in a way that we can make K the subject, and then we can input that value of K back in this equation then, and that will give us Vb. Let's try that. So if I input Vb equal to Ku minus U, what happens? On the left side, I have 50 Ku squared plus 50 into Ku minus U whole squared. On the other side, we've got 130 Ku squared plus 32.5 U squared. Now let's simplify this. It becomes 50 Ku squared. It is again going to be an issue because we are going to have K squared U squared in this case, and that is going to be a problem. Actually, let's try this. Plus 50 into K squared U squared minus 2Ku squared plus U squared. And then on the other side, we have 130 Ku squared plus 32.5 U squared. Acha. Now this simplifies to 50 ku squared plus 50 k squared u squared minus 100 ku squared plus 50 u squared, that equals 130 ku squared plus 32.5 u squared. Now we simplify this further and see what that gives us. We've got some ku squared terms. This is ku squared, this is ku squared, this is ku squared. They simplify to, if we bring that to the left side, minus 50 and minus 130 minus 180 ku squared and 32.5 u squared and 50 u squared. If we bring them to the left side, that gives us 17.5 u squared, and we also have 50 k squared u squared. That equals 0. Okay, now you see you've got u squared in all the terms. You've got u squared in every single term, right? U squared in every single term. So that also gets eliminated because we know u is not 0. So we can divide the whole thing by u squared. That also gets cancelled, and we're left with minus 180k plus 17.5 plus 50k squared, and that is something a lot simpler now. 50k squared minus 180k plus 17.5 equal to 0. That's a quadratic equation. Minus into minus 180 plus minus square root of minus 180 whole squared minus 4 into 50 into 17.5 whole divided by 2 times 50, and that will give you some value for k. You can see what that turns out to be. Menu equation polynomial degree 2 50 minus 180 17.5. One value of k that we're getting is 7 over 2 or 3.5, and another value of k that we're getting is 1 over 10, which is 0.1. Okay, now these are the two values of k that we're getting. Now what did they say about k? Do we have any information about k? Masses are k and m respectively. They're freedom on a straight line. 35%. Okay, so these are two possible values of k that we're getting. Now let's input them back there. There are two possible values of k that we're getting, but remember VB was ku minus u. It was ku minus u. You can input both of them because there's nothing given in the question that tells us whether k is positive or negative. However, if you input those values of k now in this, if you input 3.5, you get 3.5 u minus u, and that gives you 2.5 u. If you input 0.5, 0.1, that gives you 0.1 u minus u. Now this turns out to be negative 0.9 u, and you know that's not possible because they told us both particles move in the same direction as A's original motion. So if A is moving to the right, B is also moving to the right. So its velocity cannot be negative. That's why that's not possible. And the velocity of B that we end up getting therefore is 2.5 times u. So it was not momentum. It was not momentum that was complicated here. It was this algebra, right? Too many unknowns here, too many unknowns. And that took too much time. That's why it was 8 marks. Very unlikely that if you're stressed at the end of the exam, you'll be able to figure this out, but that's okay. That's what threshold is for. That takes care of it. Okay, that was part A. Let's look at part B now. That looks a bit more complicated. It's given instead that m is equal to 12. So now we know the value for m. The particles are released from rest with a string dot. Use an energy method to find the speed of the particles when each particle is moved 0.6 meters. You may assume that this occurs before A reaches the pulley or B reaches the ground. We've done a similar question before as well. When they say energy method, that means work energy principle. So work done by the driving force, that is equal to change in kinetic energy. plus the change in potential energy plus work done against resistance. This is what we are going to use here. What I'll do is I'll just copy that diagram here. So we have that in front. In your exam, you will be annotating using a pencil so that you can edit anything that you've done in the first part. You won't have time to make new diagrams every time. So just edit that same one after you're done with the first part. Okay, this is the situation. Acha. M is equal to 12 now. Particles are released from rest with the string taut. In which directions are the particles going to move? It depends on the value for M. M is 12. That means in this direction, we have a force of 12 acting. What about along the surface? What is this force? You'll have weight component acts vertically downwards, right? Which is 65. That component is going to be 65 sine alpha. 65 sine alpha. See what that value turns out to be. Sine alpha was 5 over 13, I think, right? Sine alpha is 5 over 13. Yeah. Cos alpha was 12 over 13. This is 5 over 13 and cos alpha is 12 over 13. Okay. 65 sine alpha. Evaluate this. What do you get from this? 25. Okay. So the force in this direction is 25 Newton. And this direction is 12 Newton. Now, are we sure which direction they're going to move in? Still? Are we sure about it? Can we see anything in which direction the particles are going to move? Particles are released from rest. You cannot assume that it's pulled down. You cannot do that. You cannot assume that. Acha, I'm sorry. Weight was 120 here, not 12. This was 120. Yeah, that's 120. That's not 12. This is 120. Now we need to see if this 120 is sufficient to counter this 25 plus any friction that is also going to act on this. What's the value of friction going to be? Friction acts in this direction. It's the same mu and the same r. We found that the friction value was this 0.4 into 60, and that will still be less than 120. That will still be less than 120. So that tells us that B is going to go down and A is going to go up. That's the logic. But yes, even if you read the question statement, that gives you a hint. That gives you a hint that A is going to move up and B is going to move down, because they are saying this occurs before A reaches the pulley. So that means they are saying that A is going to move in the upwards direction, but it is not going to reach the pulley. So if you can't figure it out using the weights directly, then that is basically giving you a hint as well. You can use that as well. Okay. Acha, now what do we do then? We understand this now. The forces acting in these directions. We have to use work energy principle, look at the whole system. Look at this whole system and see what forces are acting on this. Is there any driving force? The system is moving in the downward direction, right? B is moving down, A is moving up. Is there any external force acting on the system that's driving motion? No. Is there any External force acting, that is opposing motion. Yes, there is friction. So that is going to be considered. There is friction acting on A that is acting in this direction. So there is friction. Now, how much do the particles move? The particles move 0.6 meters. Okay, particles move 0.6 meters. So what will be work done against resistance? What will be work done against resistance? We already know the value for friction, right? Friction was equal to mu times r. Mu is still the same. Mu is 0.4. R is still the same as well. R is 60. So nothing has changed there. That was 24, right? So work done against resistance, that would be 24. That's the friction value multiplied by the distance traveled, which is 0.6. So we know this as well, work done against resistance. The problem is change in kinetic energy plus change in potential energy. What about this now? The particles were released from rest. They were released from rest, and we need to find the final speed of the particles. So what about the change in kinetic energy? Then half into, if you're considering the whole system, since they're both going to be moving at the same speed, kinetic energy can be calculated together. You can do it separately as well if you want. You can do it together as well. If you do it together, half m, what's the total mass? The total mass is 12. That's the total mass of the system into v squared minus 0 squared. That's the change in kinetic energy plus the change in potential energy. Potential energy change is going to be different for both the objects. That is going to be different for both the objects. So we'll have to, the change in height is different, right? So that cannot be calculated together. How will it be same speed? Because the particles are connected. The string is taut. As long as the string is taut, they move at the same speed, right? Because they're connected by the string. So whatever speed one particle moves at, the other has to move at the same speed as well, because they're connected. Friction is just going to slow both of them down. Okay, friction is going to slow both of them down. But they will both be moving at the same speed because they're connected by a string that is taut. Okay, now change in potential energy. What about B? B is moving down by a distance of 0.6 meters. So it goes down by a distance of 0.6 meters. mgh for G, mass is 12. 12 into 10 into change in height, which is negative 0.6. That's for B. It will be reducing, right? So we need to have a negative sign. You can have the negative sign here. You can have the negative sign here as well. That's your choice. But it must be negative, right? The change in potential energy for B. What about A? A is moving in the upwards direction. A is moving in the upwards direction. Mass of A is 6.5 into 10. Why were it so big? I need more space. What about the change in height for A? A is moving in the upwards direction. It travels a distance of 0.6 meters in this direction. Let's suppose this is 0.6. How do you find the change in height? Using trigonometry. This angle is alpha. You can find the change in height for A. Using trigonometry, it will be HA over the hypotenuse, which is 0.6. That equals sine alpha. We already have this value of sine alpha. That will give us some change in height. 0.6 into sine alpha. Sine alpha was 5 over 13, and that will give you some value. Okay. What do we get for this? 3 over 13. So change in height is 3 over 13. Change in height for A, that is 3 over 13. We've got this as well. So we can put that here now. Change in height for A, 3 over 13. And that is going to give you the value for B. You can see what that is. 18.5 divided by 2, that is 9.25 V squared. Simplify the rest of it, minus 72 plus 6.5 over 13, that will become 2, right? And the denominator, 30 over 2, that's 15. And then 24 into 0.6, you said that's 14.4, right? 24.06, 24 into 0.6, 14.4. And now find the value of V from this. You can see what that is. 72 minus 15 minus 14.4 divided by 9.25, square root of that. And V turns out to be 2.146, which rounds off to 2.15 meters per second. And that's the speed that we were looking for. Makes sense, right? More questions, and they look like bigger questions now. Question number 5 from this paper. Let's do this. A van of mass 2,500 kilograms is traveling at speed v meter per second, and it experiences a resistance force of kv squared. The constant power of the van's engine is 62.5 kilowatt. We've got the mass of the van. Power is 62,500 watt. Yeah, sorry. Achha, power is 62,500 watt, and we're also given the resistance force of kV squared. Steady speed means constant speed. And that means the speed when acceleration is 0. This constant speed that the van could maintain while moving along a straight horizontal road is 50 meters per second. Okay, the steady speed is 50 meters per second. So that k is equal to 0.5 and find the acceleration of the van when its speed is 25 meters per second on the straight horizontal road. We've got something related to power given. They're asking us for acceleration. Does that remind you of something? We've got velocity there as well. Power equals driving force into velocity. That's one equation that we can use for power. And this is going to be used together with another equation, which is Newton's second law of motion, F equals ma. Right? That's where acceleration is going to come from. Now, it's a horizontal surface, right? Yes, horizontal road. So we can say this is the van. What are the forces acting on the van? In the forward direction, there's driving force. There is resistance of kV squared that is going to oppose motion, kV squared. Is there any other force acting? Not really. These are the only two forces that are acting. Power is 62,500. Let's put that here. Driving force, we don't know what that is for now. Velocity is 25. Okay, we can find the value of driving force from this. What's the value of driving force? Driving force is 62,500 divided by 25. What's the number that we get from this? Has anyone done this? 2,500. Wouldn't we be 50? I'm sorry. Acha, sorry. I read the wrong value there. This is actually when they're asking you to find the acceleration when the speed is 25. I'm sorry, this is 50, not 25. We're talking about this scenario where the speed is 50. 62,500 divided by 50, what's that number? 1250. Okay, thank you. 1250 Newton. Now at this particular point, what we can do is we can find the value of K now using this particular point. Forward force is driving force. Backward force is resistance, which is kV squared, equals mass into acceleration. Since they talked about steady speed here, acceleration is going to be 0. So the right side is 0. Put this value of driving force there, 12,050 minus K into V. V is 50. So 50 squared, that equals 0. And that will give you a value for K. You can see what that is. 1250 divided by 2,500. That is going to be 0.5. That's what you wanted to show there. K equals 0.5. That's one thing that we wanted to do. Now they're saying at another point, when the speed is 25 now, that's another instrument. When the speed is 25, we need to find the value for acceleration. Now, the power they said is constant. That is not changing. Power is constant. But now if the speed is different, the driving force is going to change accordingly as well, right? Power remains constant. So we apply the two formulas, the same two formulas again now. Power equals driving force into velocity. Resultant force equals mass into acceleration. The power is the same as before, which is 62,500. Driving force into velocity. Now they're saying when speed is 25, find the value of acceleration. We can find the driving force in this particular case, and that turns out to be 2500 Newton in this case. Forward force is driving force minus the backward force, which is kv squared. The value for k now is 0.5 into v is 25. So it will be 0.5 into 25 squared. On the other side, we've got mass, which is 2500 into acceleration. Let me actually write it like this first so you understand what we're doing. kv squared, that was the resistance, right? In the next step, what I'll do is I'll write down the value of driving force 2500 minus k, which is 0.5 into v, which is 25 squared. That equals 2500 times a, and that will give you the value for a. You can see what that is. What's the value of a that you get? What value of a do we get from this? 0.875. 0.875, is that exact? 0.875. Okay, all right. That's the final answer that we've got. Then acceleration equals 0.875 meters per second squared. That's what we were looking for. Makes sense, right? Do we move on now? Next part. Okay, thank you. Let's do the next one now, part B. Now it says the van begins to ascend a hill. So now we have an inclined surface. It begins to ascend a hill, which is inclined at an angle of theta to the horizontal. This angle is theta. It travels along the slope. It starts at 20 meters per second. So it starts the journey at 20 meters per second at this point. Acceleration is 5a. It's not constant acceleration. Or is it constant acceleration? 5a. Depends on a, what a represents. Do we have a mentioned anywhere before in the question? No. Okay, so it depends on a. If a is constant, then this is also constant. Later on the same hill, the speed of the van is 30 meters per second at some point, and its acceleration at that point is a. Okay, so acceleration is not constant because initially its acceleration value is 5 times a, and then at another point on the hill, let's suppose this point here, its velocity is 30 meters per second. And it's ascending, so its velocity is increasing. And at this point, the acceleration value is just a. Earlier, it was 5a. Okay, that's what we are given. The power of the van's engine remains constant at 62,500 Newton. So that remains constant. That is not changing. Resistance force remains 0.5 v squared. That's also changing, right? Find the value of a and the value of theta. Now, number one, please do not use constant acceleration formulas here. They are not valid. Don't try to do v minus u over t to find the value of time, for instance, and then use power equals work done over time. They will not work. Acceleration is not constant. So constant acceleration formulas do not work. Okay. So what else do we do? We've got these 2 points, initial point and the final point. Let's start with the initial point and see what information we have about that. For the initial point, we know, let's call this point something. Let's call this point x and this point y. At the point x, what information do we have? We have power information. So let's use power equals driving force into velocity. Power is equal to 62,500. Driving force, we do not know what that is. Velocity is 20. So we can find the driving force at this particular point at the point x. That will turn out to be something. You can see what that is. Then to find the value for acceleration, we can use Newton's second law of motion. Apply Newton's second law of motion along with this. Now, what are the forces that are acting? Let's represent all the forces that are acting. I'll do that in the middle somewhere. What's the weight? Mass of the van was 2500. Now, weight component is going to be important here because it's an inclined surface. One component will be acting along the surface as well. This is the weight, 2500 Newton. Okay. Then what else? Weight is 2500 Newton. There is normal reaction, but reaction is not important here. If you want, you can represent that, but that's not going to be used anywhere because there's no friction, right? What else? There is going to be driving force. The van is ascending, so there is a driving force in this direction. There is resistance. Do you have resistance still? Yes, 0.5 v squared. We still have resistance that opposes motion, 0.5 v squared. These are all the forces that are acting on this object, on the van. Now, weight is the only force that is not parallel or perpendicular to the surface. So we have to resolve weight. What are the components of weight going to be? One component of weight is going to be in this direction, which is going to be equal to r, but we don't need that. The other component in this direction, that is going to be, way to write that, 25,000 sine theta, right? If this angle is theta, we know this angle here is also theta, right? So this component of weight acting in this direction, that is 25,000 sine theta. Now we just have to apply Newton's second law of motion along with that power equation, and that will give us the unknowns that we're looking for. Along the surface, the forces that are acting are driving force, 0.5 v squared, and 25,000 sine theta. Apply Newton's second law of motion. Forward force is driving force. Backward forces are 0.5 v squared and 25,000 sine theta. That should equal mass, which is 2500, into acceleration. They told us that the acceleration at the bottom was 5 times a. So 2500 times 5a. This is what we end up getting. Now, from the first equation, we're saying the driving force turns out to be 3125. Input that in the other equation, it becomes 3125 minus 0.5 v squared. The value for v was 20 at the bottom, this point here. I call this point x and this point y at the top. Squared minus 25,000 into sine theta. Did they give us a value for sine theta? No, we have to find theta. Leave it as it is. Equals 2500 into 5. That will give us a 12500 times it. Well, this is one equation that we're getting in terms of theta and a. Let's simplify the left hand side. We get 3125 minus 0.5 into 20 squared, which is 400. 2925 minus 25,000 sine theta. That equals 12,500 times a. This is one equation that we're getting. Now, do exactly the same thing at the point y as well, right? Exactly the same thing, just the values are going to be different. Make those same equations at the point y, the point at the top as well. Now, what is changing there? The speed is changing. So instead of 20, you would have 30 now. And resistance is going to be different because you also have speed involved in this. And the rest of it is going to be the same. Acceleration would also be different, right? What I'll do is I'll just copy this part from here. Okay. Okay. At the other point now, at the top, this is the information that we've got. The power is the same as before. What about velocity? Velocity at that point becomes 30. That will give you another value for driving force. What's that? What's this driving force value? 6 to 500 divided by 30. That's 6250 divided by 3. Okay, let's just keep it as it is. 6250 divided by 3. Now put this in the other equation. 6250 divided by 3 minus 0.5 into 30 squared minus 25,000 into sine theta. That equals 2500, which was the mass, into acceleration. Acceleration at that point was a. So on the right, we've got 2500 times a. This is another equation that we end up getting now. This number minus 0.5 into 30 squared, which is 900. We get 4900 divided by 3 minus 25,000 sine theta. That equals 2500 times a. We have these two equations, solve them simultaneously, and that is going to give you the values of theta and a. Okay. Now, how do we solve them simultaneously? From the first equation, I could say 25,000 sine theta, that equals 2925 minus 12500a. From this equation, I can say 25,000 sine theta, that equals 4900 over 3 minus 2500 times a. Now we've got 25,000 sine theta on one side of these equations. So we can just equate the other sides, right? Equate both of them. Or you can divide by 25,000 and then equate both of them. That's the same thing. Now, what do we get from this? 2925 minus 12500a, that equals 4900 divided by 3 minus 2500 times a. And I can find the value of a from this, see what that is. Okay, so it will be 2925 minus 4900 divided by 3 divided by 10,000. 31 over 240, that's 0.129. Somebody please confirm this calculation. 0.12917. Round it off to three significant figures. They wanted the value for acceleration, right? Let's actually write down the more accurate number first, and then I'll write the decimal. 31 over 240, which in decimals is 0.129. That's the value for acceleration. Okay. Yes, that's actually better if you just use the fraction. That's better. Okay, once we've got acceleration, now put that back in this, maybe, or in this. Any of them will work. What do you get from that? 2925 minus 12,500 into 31 over 240. I'm putting in this equation. That equals 25,000 into sine theta. You can see what value of theta you're getting from this now. That will be your final answer. Okay, 2925 minus 12500 multiplied by 31 divided by 240 divided by 25,000, and then sine inverse of that. That's 3.0 degrees. That's our final answer for the angle. All right. The first part was not that complicated. Let's look at the second part now. Now they're saying it's given instead. Now, whenever they say it's given instead, what that means is whatever we did in the first part, that's not applicable anymore. Okay? BC is rough now. The surface on the right side, that is rough. That means there's also friction now on the right side. The work done against the frictional force when Q moves 2 meters down the plane is 1.8 joules. You should assume that P does not reach the pulley, so there's no collision with the pulley, and that Q does not reach C, so Q also does not reach ground. Use an energy method to find the speed of Q when it has moved 2 meters down the plane. Now, whenever you see energy method in any question, what they're talking about is the work energy principle, okay? Or conservation of energy if there are no external forces. If there's no driving force or resistance, in that case, you can use conservation of energy. But if there is a driving force or resistance, then you use work energy principle. Yes, even if they do not mention that the particle does not reach the pulley, you will not find any question in past papers where there is going to be a collision between a particle and the pulley. Because the problem with that collision is it's not going to be head on, right? So, because it will be at an angle, right? If the particle collides with the pulley, they are at different angles, and that is not part of your syllabus. In momentum, the collisions that you have, they have to be head on, right? They can't be at an angle. So, such a collision will never happen in your syllabus because you cannot handle that. Okay. Achha, energy method. What is energy method? Work energy principle. Let's write that down here. What does the work energy principle say? Work done by the driving force, that is equal to change in kinetic energy plus the change in potential energy plus work done against resistance. You just have to input values in this and you'll get the result. Okay, work done by the driving force, that equals change in kinetic energy plus the change in potential energy plus work done against resistance. Now, in work energy principle, when you have objects connected like this, it's a good idea to just consider the whole system together. On the whole system, is there any driving force? Is there any driving force? Anything that is making the objects move down the plane? Apart from weight. Remember, weight is not considered as part of driving force, right? So there's nothing apart from weight that is making the object move down the plane. So there's no driving force then. We would say the driving force is therefore zero. So that means work done by the driving force, that's also zero. Then what about change in kinetic energy? Change in kinetic energy. What about this now? They start from rest. They start from rest. And we need to find the speed when the particles have moved 2 meters down the plane. So final speed you can say is v, initial speed is 0, right? So what's the change in kinetic energy? Half into m into v square minus u squared. Since both of them are moving at the same speed because they're connected by a string, we can consider both of them together. You can do them separately as well if you want, or do them together. For P, for instance, the mass is 0.3. For Q, the mass is 0.6. You could say 1 over 2 into 0.3 plus 0.6, that's the total mass, into V squared minus 0 squared. That's the total change in kinetic energy. You could do it like this if you wanted. You could also do them separately. So you could say 1 over 2 into 0.3 into V squared minus 0 squared for P, and then 1 over 2 into 0.6 into V squared minus 0 squared for Q. Both of these are fine. Okay, you can do any of them. Okay. So this is change in kinetic energy. Work done against resistance, what's that? They gave us that the work done against friction is 1.8 joules. So that is also covered. We know what that value is. We can just to put 1.8 there. The problem is change in potential energy. What's the change in potential energy going to be? That's the tricky part, right? Change in potential energy. So there's a question. If we are finding speed of Q, why are we using mass for both of them? When we are applying work energy principle, we're talking about the whole system, right? We can't just apply it on Q only because then there'll be too many unknowns. We can actually do that as well. We can actually do it for Q separately as well if you want. In that case, we'll have to consider T as a driving force. So there are two ways of doing this. In this case, I'm using the more general method that will actually use in most of such problems. But I'll tell you an alternative. You could apply Newton's second law of motion on Q only as well. That might give you the result as well. Let me think about it. In that case, T would be considered a resistive force. Do we know the value for T? Do we know the value for T? No, that's not relevant anymore. So I have to find the value of T, and that will be too many unknowns. Okay, yeah, so we can't do that. There will be too many unknowns. If we apply it on only Q, we would have too many unknowns. So what we are doing is we are applying con work energy principle on the whole system. The benefit of that is we would not have to consider the tensions because they kind of cancel out. So we're just talking about the whole system. The whole system, when we consider that, we have to consider both P and Q. They are both going to be moving at the same speed. If one is moving at V, for instance, the other is also moving at V. So the total change in kinetic energy in the system, that is going to be half into sum of their masses plus V squared into V squared minus 0 squared. Now, as I said, you could do it separate together like this or separately. Both of them will be fine. Acha, we'll talk about the height. We'll talk about the height. Kinetic energy part is done, right? Acha, let's talk about change in potential energy. Change in potential energy. Now, for change in potential energy, we need the change in height, right? We have their masses, we have their g, that is 10. What about the height? The change in height for both of them is not going to be the same. Why? Because the angles are different. One of them is 30 degrees and the other is theta. So along the surface, yes, both of them are going to be moving 2 meters, but perpendicular, vertical change in height, that is going to be different for both of them. So we would have to find the height, change in height for both of them separately. Now, how do we do that? Let's suppose Q moves 2 meters downwards. I'll draw that triangle here. So Q moves 2 meters downwards like this. This is Q. It moves 2 meters downwards. This length is 2. This angle is 30 degrees. Now, if it moves 2 meters downwards, what's the change in vertical height? Can we find that? Let's call this HQ, change in height for Q. We can use sine ratio. HQ over 2, perpendicular over hypotenuse, that equals sine 30. And that will give us that HQ is equal to 1. 2 sine 30, that is going to be 1. So change in height for Q is 1 meter vertically downwards. 2 meters because they told us uh, find the speed of Q when it has moved 2 meters down the plane. Okay, Q moves 2 meters down the plane at that particular point, at that particular instant, we want to find the speed of Q. So if it moves 2 meters down, the change in vertical height is 1 unit. And remember, it's decreasing. The height of Q is decreasing like this. The same thing happens with P as well. P is moving up the plane on the left side. So we can say it goes like this. Now, if Q is moving 2 meters down the plane, P would be moving 2 meters up the plane because they're connected. What about the change in height? This angle is theta. Let's call this HP. It will turn out to be HP over 2 equal to sine theta. Now, they gave us that the value of sine theta is 0.4. So HP equals 2 into 0.4. HP turns out to be 0.8. That's the change in height for particle P. Okay, we found the change in height for both of them. Now we can apply work energy principle. What's the change in potential energy for P? mgh, mass of P was 0.3 into g, which is 10, into change in height for P, that is 0.8, plus change in potential energy for Q. What would that be? mass 0.6, G 10. For Q, the height was decreasing. So the change in height will be considered negative. We will say this is -1. Now we solve this equation and that will give us the value for V. Yes, so for Q, the change in potential energy is going to be negative. For P, the change in potential energy is going to be positive. Now we can simplify this and see what this gives us. 0.9 over 2, that's 0.45 V squared plus 3 into 0.8. What's that? 2.4, I think. Minus 6 plus 1.8, that equals 0. And that will give you the value for V. You can see what that is. V is equal to under root 4, which is 2. So you're saying it's 2? Okay, so V equals 2 meters per second. That is what we were looking for. Now, this is something that happens very often in recent papers. You'll have two inclined planes, different angles. The change in height for both of them is going to be different. And how do you find that change in height? Using trigonometry length. Okay? Any issues with this? Why is the work done by the driving force 0? Because when we talk about this whole system, what is making the system move in this direction? What force is making the making the system move in this direction? 6 sine 30, it's the weight component. Weight is not considered a driving force. So apart from weight, there's no other force that's acting. So the driving force is 0 for that reason. Okay. So, weight is not considered part of driving force. So that will not be considered. That was question number 6. The next one is question number 7. It says a car has mass 1200 kilograms. When the car is traveling at a speed of v meters per second, there is a resistive force of magnitude k times v. There is a resistance kV. Mass is 1200. Speed is v. Maximum power of the car's engine is 92.16 kilowatt. In standard unit, that will be 92160 watt. Now, the car is traveling along a straight level road. So it's a horizontal road. The car has the greatest possible constant speed of 48 meters per second. Show that k is equal to 40. Okay, now what is power given by? Power is equal to driving force into velocity. What other information do we have? Resistance, that's a force. We can use it together with, so k is equal to 40. Yeah, we can actually find this directly. Power, maximum power of the car is this, and the maximum speed of the car is 48. If we use this together with Newton's second law of motion, okay, this is constant speed. Okay, all right, I did not read that. This is constant speed. Okay, all right. So what we can do is we can say power is 92160. Power is 92160. That is equal to driving force into velocity, that is 48. And that will give you a value for driving force. You can see what that is. Now, forward force is driving force in this case, backward force is resistance. That equals mass into acceleration. Since they're talking about constant speed, acceleration is going to be 0. So on the right side, we get 0. The driving force value that we get on the left side, what's that? From this, we can say driving force is equal to R, right? So we can equate it to that. 92160, that's 1920. Okay, 1920. That means R is equal to 1920. They said resistance is K times V. We'll actually input that directly here as well. Just put driving force minus kV, that equals kV. kV equals this, and the value of K is equal to 1920 over 48, which should turn out to be 40. Okay. Now, all of that working is not necessary. Those of you who understand that since they're traveling at constant speed, that means acceleration is zero. So the forward force and backward forces are going to be equal to each other. From this equation, you could directly input kV in place of driving force here. In this very step, you could input driving force equal to K times V. So you could reduce this working. You could say driving force is K into V directly. The value of V is also known, right? You can input that here, K into 48 into 48. And that will give the value for K, which is 40. Now, just be careful. Some people end up making this mistake that they always just put driving force equal to resistance whenever they say constant speed. In some cases, what happens is we have some other forces as well. So that's why I generally try to do it every single time that I input values in this equation. So that you make a habit of this, that this driving force equal to resistance is coming from this equation, because what happens is sometimes there's another force as well, especially when there's an inclined surface. There will be a weight component as well that you have to consider. A lot of people end up forgetting that there might be some other force given as well. So it's not always going to be the case that the driving force is equal to R in case of constant speed. When there are other forces involved, you have to consider those as well. Okay, just keep uh, just take that into account. As long as you do that, you could skip that working in this part if you wanted. Okay. Achha. No, we do not need to write acceleration equal to zero necessarily. Just equate the forward forces and backward forces. In this case, that will be fine. Okay. All right. That was part A1. Now part 2 says, at an instant when its speed is 45 meters per second, find the greatest possible value of acceleration of the car. Okay, now again, driving force is equal to power is equal to driving force into velocity. This is one equation that we've got. Now the speed is not constant. Now the speed is not constant, so driving force is not equal to resistance. Forward force is driving force. Backward force is resistance, which is K times V. That is equal to mass. Mass of this car is 1200 times acceleration. This is one equation that we've got. We can input the value of K and V here as well now. The value for K, we found that in the previous part. That's a constant, right? 40 into V, which is 45. This equals 1200 times A. Now from the first equation, we could say, what is power going to be? If we're looking for the greatest possible acceleration of the car, the greatest possible value of acceleration is going to correspond to the greatest power that is generated, which is 92160. We can input that here. The speed at this point is 45. Input that in your calculator, you'll get a value for df. You can see what this is. Input that in the other equation then. What's the value of driving force that we get? 92160 divided by 45, that's 2048. Thank you, 2048. Input that in the other equation, and now the other equation becomes 2048 minus this, and from that you can get the value for A. You can see what that turns out to be. 31 over 150. In decimals, that is 0.207. Okay, thank you. That's the final answer that we get. All right, no problem. Chale, let's do the last one now. No, there's another part of this. The car now travels at a constant speed up a hill. Okay, now this is that case where driving force and resistance are not equal. You can say forward forces and backward forces are going to be equal to each other, which would also include the weight component. The surface is now inclined at an angle of sine inverse of 0.15. Find the greatest possible speed of the car going up the hill. So again, we'll use the greatest power value from there. It's an inclined surface. It goes like this. Let's call this angle theta. So what we're given is the value of theta is sine inverse of 0.15. So what's the value of sine theta going to be then? Sine theta is going to equal 0.15. Okay. Now, let's suppose this is the car. It has some weight, 12,000. 1,200 was the mass, right? Yeah. Then it is moving up the hill, so there's going to be driving force acting up the slope like this. That's the driving force. There's going to be resistance that opposes motion. That's k times v. K is 40, so you can say 40 times v. That's your resistance value. What else? There's normal reaction, yes, but we don't need that because there's no friction involved, so we can ignore that. Weight components, there's going to be one component acting in this direction. There's one component acting in this direction, but we don't need that. The other component is going to act down the plane. That will be 12,000 sine theta. Okay. Now along the surface, we've got these forces acting, driving force 40V and 12,000 sine theta. These are the forces acting down along the surface. Apply Newton's second law of motion and use the power formula along with that. Power equals driving force into velocity. Now, what was the value for power that we had? Power was equal to 92160. 92160. That is equal to driving force, which we do not know what it is, into V, right? This is what we get. This is one equation that we're getting. Then we make another equation. Resultant force equals mass into acceleration. What's the forward force? The forward force is driving force. Backward force is 40 times V and 12,000 sine theta. What was the value of sine theta? 0.15. 12,000 into 0.15, that equals mass, which is 1200 into acceleration. That will be 0. Why is that going to be 0? Is acceleration going to be 0? Why did I say it's 0? It's not constant. Actually, it's constant speed. They do say that. No, no, they. So they said it's moving at constant speed, but then it says greatest possible speed after that. Okay, so I was actually looking at this greatest possible speed. Even if they did not mention constant speed, greatest speed also tells us that acceleration is 0, right? When velocity is at its maximum value, in that case as well, acceleration is 0. So even if they had not mentioned this also tells us that, right? At maximum velocity as well, since the velocity time graph would look like this, for example, this would be the maximum point, gradient would be 0. Gradient of velocity time graph is acceleration. So if speed is maximum, acceleration is going to be 0 for that reason as well. Achha. So on the right side, we just have 0 then. Find the value of df from this. That will be in terms of, what are we looking for? V, right? Okay. It will be in terms of V. You can see what that is. 12,000 into 0.15. That's 1,800. 1,800 plus 40 times V. That's another equation that we're getting. Just give me a second. Okay, I'll be back in a minute. Okay, so we are getting driving force equal to 1800 plus 40V. Now we could input that in the other equation and you'll get a quadratic equation. 92160 equal to 1800 plus 40V times V. This simplifies to 40V squared plus 1800V minus 92160 equal to 0. That's a quadratic equation. You can input this whole thing on your calculator directly. Can we actually divide it by 40? 1800 divided by 40. That's 45. 92160. Yeah, okay. So this can be simplified to V squared plus 45V minus 2304. But it's not necessary that you do it. You can do it. You can input this directly in your calculator and directly in the quadratic formula. And then in your calculator after that, minus 45 plus minus square root of 45 squared minus 4 into 1 into negative 2304. Whole divided by 2 times 1. Now you input this in a calculator and see what that gives you. What's the value of speed that you're getting? 30.51 and negative 75.5. Now, negative is of course not possible, so we ignore that. And the only possible answer is 30.5 to 3 significant figures. And that's our final answer. That inshallah. 7 part B. It says use an energy method to find the speed of the particles at the instant when they are at the same vertical height. How do we think about this now? Can you tell me the answers for the first part? Okay, thank you. A equals 1.06 and T equals 5.53. Okay, tension we will probably not need in this case. Let me copy that diagram. It's a common question that is coming repeatedly in recent papers actually. So it's a good idea to discuss it as well. Abdullah, first part is just Newton's second law of motion. You just represent all the forces acting on both the particles. Apply Newton's second law of motion on both of them. So for Q, we've got weight acting downwards, 5 Newton, tension acting upwards. For P, we have weight component acting here. Weight in the downward direction would be 25. In this direction, it becomes 25 sine 30. Here we've got tension. It's a smooth plane, right? Is it a smooth plane? Yeah, it's a smooth. Does it say anything? Anything? Plane is rough. Okay, no, plane is rough. It's a rough plane. It's a rough plane, so there's friction as well. P slides down the plane, so friction is going to act up the plane in this direction. Other weight component is going to be in this direction, 25 cos 30. There will be normal reaction in this direction. These are all the forces. Apply Newton's second law of motion in both of them. R is going to equal 25 cos 30. You can put F equal to mu R to find the value for friction, and then apply Newton's second law of motion. 25 sine 30 minus F minus T should equal 2.5 times A, and T minus 5 should equal 0.5 times A. You'll get two equations, right? We're not using equilibrium, we're using Newton's second law of motion. Perpendicular to the surface, there will be no motion. So these forces are equal. Along the motion, we are applying Newton's second law of motion. F equals ma. Okay. All right, so let's look at part B. Use an energy method to find the speed of the particles at the instant when they are at the same height. Now, what happens is P is moving down the plane and Q is moving up the plane. The total distance between the vertical heights is 2 meters. At some point, their heights become equal to each other. At some point, their heights become equal to each other. They are at the same height. Let's say until that point, Q has traveled this distance and P has traveled this distance down the plane. Okay. And now they are at the same height, like this. Can we assume that they traveled the same distance? 2 meters is the total distance, so it will be 1 meter and 1 meter. Can we assume that? Can we assume that? We cannot assume that, right? Because Q is moving vertically, P is moving along the plane. So the distances moved will be different. Okay. Now, if we want to use an energy method means work energy principle. We just have to input values in this work energy principle. Work done by driving force, that is equal to change in kinetic energy plus change in potential energy plus work done against resistance. Now, let's suppose Q moves up by X units. We need that change in height. Why? Because for change in potential energy, we need the change in height, right? So let's find how much distance Q moves in the upwards direction and P moves in that direction. Let's call this distance X. Then this would also be X, right? Whatever distance Q moves in the upwards direction, that will be the same distance that P moves down the plane. What about the change in vertical height for P? What would that be? Change in the vertical height of P. We'll have to use trigonometry for that. We have a right angle triangle here. In this right angle triangle, this angle, so I'm talking about this triangle, this red triangle, this angle is 30. If I were to enlarge this triangle and draw that on the side, it looks something like this. The hypotenuse is X. This angle is 30 degrees. And we want to find this H, the height that reduces for the particle P. Can we find H in terms of X? Perpendicular hypotenuse, what's the ratio between them? Sine H over X equals sine of 30. And that gives us that the height is sine 30 is 0.5, so that's 0.5 times X. That's the change in height that we get. So that means if Q moves up by X units, P moves down by 0.5 times X, or you can say half of X. Now, can we find the value of X? We know this distance is X now. And then this distance is half X. The total is 2 units. So we could say x plus half x equals 2 units. That will give us the value for x. 3 over 2x equals 2, x equals 4 over 3. So q moves up by a distance of 4 over 3 and p moves down by a distance of 2 over 3. That's the result that we end up getting from this. So q is moving up by a distance of 4 over 3 and p is moving down vertically by a distance of 2 over 3. Is that clear to everyone? What did we just do? This complete distance between P and Q vertically, that is 2 units. If we say Q is moving up by X units until it reaches the same height as P, then using that right angle triangle, we figured out that H is moving down by half X units. The total we know is 2 units. So X plus half X, that should equal 2. And that gives us the value for X. Is that okay, Rita? Look at the question. They're saying, find the speed of the particles at the instant when they are at the same vertical height, right? That's what they're saying. जब वो same, we have some people who don't understand Urdu. We have some point at which the height becomes the same. The height becomes the same. ठीक है? यहाँ पे the height becomes the same. Until this point, Q has moved up by a distance of x units. हम कह रहे हैं इसको हम x assume कर लेते हैं कि Q कितना ऊपर मूव किया, इसको हमने x assume कर लिया. अब उसी पॉइंट पे P would have traveled in this direction by the same distance which is x. जितना Q ऊपर जाएगा उतना ही P along the surface नीचे आएगा, क्योंकि वो दोनों कनेक्टेड है. जितना P ऊपर मूव करेगा उतना ही Q along the surface नीचे मूव करेगा. ओके अब अगर वो x नीचे मूव कर रहा है, हमने ये ट्राइंगल यहां पे बनाई टू फिगर आउट कि ये वर्टिकली कितना नीचे जाता है यूजिंग राइट एंगल ट्राइंगल. हमने राइट एंगल ट्राइंगल बना के हमने कहा कि ये x है, तो वर्टिकली ये कितना डिस्टेंस नीचे जाएगा. राइट एंगल ट्राइंगल यूज करके वी फाइंड द वैल्यू फॉर h, दैट्स हाफ x. अब हमें पता चला अगर q x यूनिट्स ऊपर जाता है तो p उस पॉइंट से हाफ x यूनिट्स नीचे आता है, और इन दोनों का टोटल उसने बताया हुआ था कि 2 है. इनिशियली जो उनके दरमियान में वर्टिकल डिस्टेंस था दैट वाज 2 यूनिट्स. तो हम ये कह सकते हैं दिस x प्लस दिस हाफ x दैट मस्ट इक्वल टू, और उससे हमारे पास x की वैल्यू आ जाती है. You'll have to be specific. If you still don't understand it, let me know exactly what specific part you don't understand. Okay, good. All right. Chale. Let's move on. We found the value for x. How can a business student possibly figure this out? What does it have to do with business? Or it's not physics, it's simple maths, it's trigonometry. Just trigonometry. यहाँ अभी तक तो मैकेनिक्स कुछ थी भी नहीं, यहाँ पे बेसिक ट्रिग्नोमेट्री यूज कर रहे हैं. अच्छा, they told us this distance is 2 units. Initially, the vertical distance between P and Q was 2 units. They told us. So by the time the distance becomes the same, whatever distance Q has traveled in the upwards direction and P has traveled in the downward direction, their sum should be 2. Okay, so let's discuss it at the end then. If you still don't get it, we could discuss it at the end of the class, inshallah. Now that we know the distances traveled in the vertical direction, work done by the driving force. In such situations, when we are applying work energy principle, it's easier to consider this whole thing as a single system. P, Q, and the string, consider the whole thing as a single system. Okay? Is there any driving force? Any force external to the system that is making the object move apart from weight? There's no external force, right? That's making the object move down the plane. So there's no driving force. Working by the driving force, that is zero. Change in kinetic energy. Change in kinetic energy. We could do it together as well because P and Q are connected to each other. Whatever change in kinetic energy we've got for P, it will be the same change in kinetic energy for Q as well. Okay? The speed will be the same, kinetic energy will be different, but the speed will be the same for both of them. Now, we have to find that change in speed as well, because in the previous part, we found the value for acceleration. For finding change in kinetic energy, yes, we know the initial velocity, but what about the final velocity? We have to find that. Let's do that on the side as well. Final velocity, we know initial velocity is 0. Into it here. Initial velocity is 0. Displacement for both of them is x units, which we found to be 4/3. S is equal to 4/3. What else? We know the value for acceleration from the previous part as well, which was 1.06. Ideally, you should use the more accurate number than 1.06. This will give you the value for final velocity. V squared equals u squared plus 2as. Input values in that and see what that gives you. V squared equals 0 squared plus 2 into 1.06 into s, that is 4/3. Now that will give you a value for v. This will be the final speed of the particles until they reach that point where the heights are the same. What does this point turn out to be? What does this point turn out to be? V is 1.6812. 1.6812. That's the value for V. So now what about the change in kinetic energy? Let's do it separately for P and 5, half into 2.5 into V squared minus U squared, 1.6812 squared minus 0 squared. For Q, it would be half into 0.5 into 1.6812 squared minus 0 squared. Now you see, half is common between them. This is also common between them. The only difference is masses. We could handle them together as well. This is one way to write it. To make it more efficient, we could also write it together like this. The total mass of the system, that's 2.5 plus 0.5. And then we could multiply by 1.6812 squared minus 0 squared. That will be the change in kinetic energy. So you can do this, do it using any of the two methods, separately or together like this. The velocities are going to be the same for both of them because they're connected by a string. Since they're connected by a string and the string is taut, whatever speed one particle moves at, the other particle is also going to move at the same speed. So the velocities are going to be the same for both of them. Is that okay? We can only consider them together because the velocities are the same. Otherwise, we would have to calculate the kinetic energy separately for them. Okay? Acha. Now, what about potential energy? Change in potential energy. Now, the height is changing differently for both the particles. So potential energies will have to be calculated separately. What about the change in potential energy for P? mgh 2.5 into 10 into change in height. How much is the height changing for B? 2 over 3 units, and it is decreasing. So we'll say this is minus 2 over 3. What about Q? Mass of Q is 0.5 into 10 into change in height. That's increasing. That will be positive 4 over 3. And then work done against resistance. Do we have any resistance in this case? Do we have any resistance? We have resistance, right? There's friction. There is friction involved. Now, do we know the value for friction? You would have done this in the previous part. Friction would have turned out to be equal to mu times R. Mu was 0.2 into R. What was the value for R? 25 cos 30. You would know the value for friction from the previous part. What was that? Value for friction in the previous part. 4.33. 5 under root 3 over 2. That's better. 5 under root 3 over 2, like this, or the under root is on the whole thing. Okay, that's the value for friction from the previous part. What about work done against resistance? Work done against resistance will be the value of that force multiplied by the displacement. Now, how much is the displacement? Force is 5 under root 3 over 2 into displacement. How much is it moving? X units. Multiply this by 4 over 3. And that is going to give you the value for V that we're looking for. You solve this equation, find the value for V. There's no unknown here. I'm sorry. When they are at the same vertical height, this was the initial velocity. I'm sorry about that. Okay, I'm sorry about that. What I did was I found the value for speed using this. We did not have to do that. They actually told us to use the energy method. This was not required. V is what we were looking for actually. So it was just V squared. We have to find the value for V because in that whole equation, there was nothing unknown. We had already found the value for V from that other method. Did not have to do that. We had to use energy method for that, right? So the final speed is unknown. We keep that as V, and that will give us the value for V. You can see what that is. Solve this equation, find the value of V from that. Now, let me repeat. What we've done is we found the change in height for both of them. Q was increasing in height by 4 over 3. P was decreasing in height by 2 over 3. Right? That gave us the change in potential energy for both of them. Change in kinetic energy, half into sum of the masses into final speed, we call that V. Initial speed, we call that 0. So V squared minus 0 squared, and then work done against resistance. Okay. You can see what value of V you get from that. Let's figure that out. 3 over 2, that is 1.5. 1.5 V squared minus 25 into 2, which is 50 over 3, plus 20 over 3, plus 20 over 2, which is 10 under root 3 over 3. And that equals 0. Let's see what value of v we get from this. 50 over 3 minus 20 over 3 minus 10 under root 3 divided by 3 divided by 1.5 on the other side, and then square root of that. That's 1.678. That's exactly what we were getting from the other method as well, right? 1.6786. So I calculated that final velocity using the constant acceleration formulas earlier. They asked us to do that using energy method. So we're getting the same value from this as well, 1.68 meters per second. That's the final velocity. And that's what we wanted to find out.